Welcome to my webinar. Today's presentation is titled Designing for Shock and Vibration Environments. This is part of the Simulation How-To webinar series that I host every quarter for customers of Digital Dimensions. Design engineers are more often ruggedizing their products to withstand shock and vibration environments. Shock and vibration loading can come from internal sources, such as motors, fans, and pumps, or from external sources such as seismic conditions, aircraft turbulence, ocean waves, wind, and so on. Shock and vibration testing is being utilized more often to optimize designs, improve product performance, reliability, and safety, to reduce costs, and also to meet regulatory specifications. Those of you designing military products will probably need to meet the mil specs for shock and vibration loading, so you'll need to do testing at some point in time anyway. Now, the most accurate way to test your products is to test them in real-world conditions. However, this testing isn't cheap, especially if you're trying to simulate an earthquake, a military vehicle in flight, or a depth charge. An alternative to testing in real-world conditions is to place your product on a shaker table. You'll need to build a working model, shake it, then see if it still works. With this type of testing, you run the risk of breaking an expensive piece of equipment, or you'll find out whether the part breaks or not, but you won't know why. This is where virtual prototyping or simulation comes into play. With simulations, you have the additional design insight into how your design is working, so you know where the strong and the weak points are before you create your physical prototype. SOLIDWORKS simulation is the class of products that allows you to validate your SOLIDWORKS designs. In this presentation, we'll use the advanced dynamics capabilities that are part of the SOLIDWORKS Simulation Premium package to simulate shock and vibration environments. The advanced dynamics capabilities include time histories, random vibrations, harmonics, and shock response spectra. We'll use a simple circuit board in this demonstration since it's small enough to let me run a number of live simulations over the next few minutes. All the load curves you see on this slide are typical inputs that you might get from a product specification, such as the mil specs. We've got a shock response spectra, a time history curve, a harmonic curve, and a random vibration curve. And we'll test for all of them in this webinar. Now, the first step in any type of dynamic analysis is to understand the natural frequencies and mode shapes of your structure, because these tell you how your structure is going to deform due to a dynamic load. So let's go into SOLIDWORKS and let's start off by doing a natural frequency simulation on the circuit board. So to do a frequency analysis, the first thing we want to do is we want to go up to the simulation menu and we want to create a study. Study is going to be like test cases, and you want to probably do a number of different test cases for each different part that you want to simulate. And you can give these different test cases different names, and this test case is going to be called frequency because we're going to do a natural frequency simulation. We'll click on the frequency option and click on OK. And you'll notice that we've got the new simulation feature manager on the left hand side. And the way it works is you basically start at the top and you work your way down to the bottom. The first folder in your feature manager is going to be your parts folder. This is where you want to tell the software what all the different parts are made out of. Notice all the different parts have material properties already assigned, and that's because the solid models already have material properties assigned to them. So we're going to skip that folder. We'll come down to the connections folder, and we will stick with the default option, which is going to be the globally bonded contact option, and we'll stick with that. And we'll come down to the fixtures folder. With the fixtures folder, we want to tell the software how this particular circuit board is attached to the outside world. So we'll click on the fixed geometry option, and we'll come up to all the different connection points where the circuit board is being attached with the connector. And we're just going to basically click on all these different surfaces, and we're going to fix all these surfaces from moving. We'll keep stepping down the feature manager. The next folder is going to be the external loads folder. We're going to skip that because you don't need an external load for a natural frequency simulation. And we'll come down to the mesh folder. I'm going to go ahead and create the mesh. We'll use the default options, but I will use a draft quality mesh just so we can run some quicker simulations. And this is what the mesh looks like. Let's change some of the properties of the solver. By default, the solver solves for the first 5 natural frequencies. Let's bump this up to 15. Let's click on OK, and let's go ahead and run the simulation. And we're done. let's turn off the simulation symbols and let's see what we got. So notice underneath the results folder we've got the first 15 natural frequencies listed. The first natural frequency is plotted on the screen, and our first natural frequency has a natural frequency of 284 Hertz. Let's go ahead and animate the simulation, and this is what your results look like. Your first natural frequency is going to represent the easiest way to bend your board. And so if you take this board and shake it around, it's probably going to oscillate at 284 Hertz with this particular mode shape. The second natural frequency comes in at 406 Hertz. Let's go ahead and animate this. The second natural frequency is going to indicate the second easiest way to bend your board. And notice that the front flap is bending. That's probably due to the larger mass of the capacitors at the front of the board. And so if you shake it around, it's probably going to have some component of this particular mode, and this particular mode again is going to oscillate 406 Hertz. Now if you look at the higher level frequencies, I'll jump down all the way to your 15th mode shape. Notice the natural frequency bumps up all the way up to 1800 Hertz. Let's go ahead and animate this. This is basically one of the bending modes of one of these little slits. This mode is much harder to activate versus some of the lower modes. It's a much stiffer mode. When you take a look at these different natural frequencies, you want to understand how the different modes are moving, and you also want to make sure that all the natural frequencies are within your input frequency range. So let me go ahead and list the resonant frequencies. And you notice that the first natural frequency comes in at 284 Hertz. My 15th natural frequency comes in at 1800 Hertz. So you want to make sure you capture enough natural frequencies that's going to cover your input range. Now most of your mil-spec frequencies are going to go from anywhere from 0 to 1000 Hertz, or sometimes 0 to 2000 Hertz. So you want to make sure you capture all the natural frequencies within your input range. In our case, we'll stick with 15 natural frequencies. The other thing you want to do is you want to take a look at your mass participation factors, and you want to make sure that you have at least 85% of your modal mass in the direction that you're interested in. So the main deformation direction is going to be the Z direction, and notice we're covering at least 95% of the modal mass in the Z direction. So 15 natural frequencies looks good for the modal superposition, which is what we're going to do next. A natural frequency analysis is also considered free vibration. That's because there's no load. And so the displacements that you're looking at are actually unreal, but these are basically normalized values to give you kind of an indication of how your structure is going to deform. If you want to find out how much they're going to deform, you have to do a forced vibration analysis. And that's going to be the next step. So let me switch back into my PowerPoint presentation. So the first forced vibration simulation we're going to do is going to be a time history analysis. Time history analysis shows the time-dependent loading and the time-dependent response of a structure. It's typically used for shock loading. So notice the two time curves or load curves that you see on the left-hand side of this slide. I've got a fast loading case and a slow loading case. We can basically add any type of time curve into your load definition and find out how your structure is going to respond. So let me show you how to do that. And let's create a new simulation study. This one's going to be a time history. So I'm going to come up to the simulation menu again. I'll create a new study. This time the study is going to be called time history. I'll come down to the linear dynamic option. Notice the different sub options down at the bottom. We've got modal time histories, we've got harmonics, we've got random vibrations, and shock response spectra. We'll start off with the time history analysis first. I'll click on OK. And notice we've got a new feature manager again on the left hand side. This is your simulation feature manager. Very similar to what we had before. And so let's just step down the feature manager. We're done with the parts folder because all the different material properties have already been assigned to the solid models. We'll skip the connections folder because we're going to use the global bonded contact option. Under fixtures, we're going to come back to our frequency study, and we're going to take the fixtures that we've already defined and we're going to drag it and drop it into our time history folder. Now let's come down to our external loads. I'll come down to our uniform base excitation because we're going to take the outside structure and we're going to shake it, and we're going to see how the circuit board is going to react. So I'm going to come down to the acceleration option, and the reference geometry that we're going to use is going to be the top of the board. I'll change the units over to G's, and I'm going to put in a multiplication factor of 1G, and notice the direction of that acceleration. And I'll click on the curve option. And at this point, the software is going to give me the ability to actually input a curve. Now, I can input the time points for each within the curve, or I can come straight into Microsoft Excel. And notice I've got a basic time history curve. It goes from 0 to 10 Gs within 1 millisecond. And what I'll do is I'll just copy the curve from Microsoft Excel. I'll come back into SOLIDWORKS and I'll paste this curve in. Now when I click on View, this is what my time curve looks like. So notice that the acceleration levels go from 0 to 10 Gs within about a millisecond, and it drops back down to 0. So I'll go ahead and click on OK there. We're done with the external loads. I want to use the same mesh that we used the last time, so I'm going to come back to the frequency study, and I'm going to take this mesh and I'm going to drag it and drop it over into my time history folder. Let's go ahead and specify some damping. And for our first 15 modes, let's use a damping factor of, let's say, 5%. Now I want to come back into the properties of my time history study. The properties folder gives us the ability to specify the number of frequencies that we want to use for the modal superposition. We're going to stick with 15 because we just found out that 15 covers at least 85% of your modal mass. I'll come up to the dynamic options, and we want to tell the software how long we want to run this for. So we're going to go from 0 to 0.01 seconds, and let's make the time increment small. We're going to make it down to 0.0001. You want to make sure that you capture at least 1/10 of the period of your highest natural frequency. And let's click on OK there, and let's go ahead and run it. Now, time histories are going to take a little bit longer than a frequency analysis or even a static analysis. That's because we're running a number of different solutions at each of the different time steps that we've specified. And again, we're running from 0 to 0.01 seconds in increments of 0.0001 seconds, or actually the time step is 0.1 milliseconds. So we're actually almost done with the simulation. We're just doing the stress calculations right now, and we are done. So notice that the maximum stress that we have here is 228,000 pascals. And so what we want to do is let's edit the definition, and let's take a look at the maximum value, because this stress level is occurring at 0.01 seconds. But the maximum stress on this board is actually going to come up to 651,000 pascals. Let's take a look at the displacements. Maximum displacement at the end time, which is 0.01 seconds, is 0.01 millimeters. Let's go ahead and probe the results. And I'm going to use my sensor option. And I've got some sensors already pre-specified at the 4 corners of the 4 chips. Let's see what our displacements look like over time. And this is what the resultant displacement looks like. So maximum displacement looks like it's going to be about 0.031 millimeters. Now let's take a look at our acceleration levels. I'll define an acceleration plot. Let's change the units to G's. And let's find out what the maximum accelerations that are going to be on these chips. So I'm going to go ahead and probe the results again. And I'll use the sensor option again, and let's take a look at the acceleration levels at the 4 corners of the 4 chips. And this is what your accelerations look like. So notice with the initial shock goes from 0 to about 10 Gs within 0.001 seconds. So notice this little sharp climb over here. Maximum acceleration at some of these chips is going to be 12 Gs. So you get a transmissibility factor of about 1.2 here. Okay, so with these results, you basically want to compare these with the allowables of your particular product. For circuit boards, typically you want to take a look at the maximum displacements and compare the maximum allowable displacements that you typically get from like the Steinberg equations. But if you're doing a stress analysis on a structural component, you want to make sure that your stress results are lower than the allowable stresses per your product specifications. So let's move on to the next type of force vibration simulation. So let me switch back over into my PowerPoint presentation. And the next type of simulation is going to be a shock response spectrum. Shock response spectrum are typically used for military or seismic applications. What they let you do is find the peak values of models' responses. They can be used instead of transient responses for things like earthquakes, wind, ocean waves, thrust, and motor vibrations. So anytime you're looking at shock conditions or you want to simulate shock conditions, there's two different ways. You can either do that with a shock time history, which is what we just did in the previous simulation, or you can transfer everything into the frequency domain and you can do a shock response spectrum where your load curve is actually going to be in the frequency domain, and it's actually going to simulate the maximum response or the maximum input load that your structure is going to see. So let me show you how to do this. I'm going to switch back into SolidWorks. And let's come up to the simulation menu again. Let's create a new study. This one's going to be called Shock Response Spectrum. I'll come back down to the linear dynamic simulation. Let's choose the response spectrum analysis option. And let's click on OK. And just like before, we're going to start at the top of your feature manager and work our way down to the bottom. We'll bypass the parts folders and the connections folders. For the fixtures, let's come back to our time history study. Let's take the fixtures that we've already defined and let's drag it and drop into our shock response spectrum. Now let's come down to our external loads. Again, we're going to take the base of the structure wherever it's connected to the outside environment, and we're going to shake it with the shock response spectrum. And I'll put in a multiplier 1G in the Z direction. And let's create a new curve. And that curve is going to be in terms of hertz. And I'm going to come back into my Microsoft Excel spreadsheet. Let's click on the shock response spectrum. Again, notice I've got a shock response spectrum that's already predefined for me, and we typically get these curves from your product specifications or your customer specifications. I'm going to copy this curve. I'll come back into SolidWorks, and I'll go ahead and paste this curve in. And I'll click on View, and this is what your shock response spectrum is going to look like. Alright, so let's keep stepping down this feature manager. The next folder is going to be the mesh folder. For the mesh, we're going to use the same mesh that we've used before. So I'm going to take the mesh from the time history study, and I'm going to go ahead and drag it and drop it. Let's take a look at the properties of our shock response spectrum. Again, we're going to use 15 natural frequencies because that covers at least 85% of our modal mass. And we'll stick with the default SRSS method for our mode combination. And let's go ahead and run our simulation. Okay, so this is done. Maximum stress here looks like it's going to be about 9.3 megapascals. Let's take a look at the acceleration plots. And this is what our maximum acceleration looks like. Let's go ahead and probe the results. And at the different chip levels, in locations, just like we got before, it looks like our maximum accelerations that we're getting here, it looks like it's about 121 or 186 Gs. So very, very high amplification with this particular shock response spectrum. And again, just like before, what you want to do is you want to take your results and compare them with the allowable results of your particular product. For circuit boards, you typically look at your maximum deflection, and in our case, our maximum deflection is 0.4955 millimeters, and you want to compare that with whatever allowable displacement you get from the Steinberg equations. Okay, let's switch over to the next forced vibration type of simulation. So let me switch back over into my PowerPoint presentation. So we just did the shock response spectrum. The next type of simulation is going to be a random vibration analysis. So random vibrations are typically covering things like non-periodic loading. This is where past history data is used to predict the probability of the future occurrences of displacements, velocities, and accelerations. PSDs are very prevalent in the MIL specs, the MIL 810 specs. So basically what random vibration simulations are, they're going to be it's basically a statistical type of analysis where when you've got this long non-periodic loading, it's very difficult to test for this with the time history. But with this long non-periodic type of loading, we can actually do a statistical type of simulation. That's what we're going to be doing. So we can take the non-periodic loading or the random vibration loading that you see at the upper right-hand corner of the slide, and we can transfer that into the frequency domain in the form of a power spectral density. And typical units for your power spectral densities are going to be G squared per hertz. And so let me show you how to do that. I'm going to switch back into SolidWorks. And let's create a new random vibration study. So I'll click on the study option, and the new study is going to be called a random vibration study. I'll click on the linear dynamic option, and let's click on the random vibration option. And just like before, we get a new simulation feature manager. This time it's called random vibrations, and we want to do the same thing that we did before. We want to start at the top of the feature manager and work our way down to the bottom. By the way, random vibrations are, if you want to compare this to a real-world example, if you want to take a look at the stresses on, let's say, on an aircraft during takeoff, typically your parts are going to be exposed to a shock loading because you get an initial impulse of load. If you want to find out how your parts are going to react once once the airplane's up in the air, then you want to take a look at a random vibration simulation, because it's not an impulsive load. It's just going to be just a random vibration loading, which is going to be non-periodic. It's going to take a while. Okay, so let's step down the feature manager. Let's skip the parts folder because we know that the materials are already defined. Let's skip the connections folder because we're going to use the default option, which is the global bonded contact. We're going to take the fixtures from our previous studies, and we're going to drag it and drop it into our random vibration study. We're going to define our external loads. We're going to use the uniform base excitation because the circuit board is mounted to some other type of electronic enclosure. We'll change the units to G squared per hertz because that's what our typical units are going to be. And I'll put in a multiplier of 1. Notice the purple arrow, which signifies the direction of our load. And let's change the units to hertz. And I'll switch back into Microsoft Excel. And I've got a random vibration curve that's already been predefined for me. This one's going to ramp up from 0 to 1 G squared per hertz between 0 and 1,000 hertz. And then from 1,000 to 2,000 hertz, we're just going to get a constant power spectral density value. So I'm going to go ahead and copy this curve. I'll switch back into SolidWorks. Let's go ahead and paste this curve in. I'll click on View, and this is what our power spectral density curve is going to look like. So it's a typical power spectral density curve that you'll get from the mil specs. So I'll go ahead and click on OK, and let's step down the feature manager. The next option is going to be the mesh option. So I'll come back to one of our previous studies. I'll take the mesh and I'll drag it and drop it to our random vibration study. And let's go ahead and take the damping from our time history study, and let's drag it and drop it into the random vibration study also. Let's go ahead and change the properties of our random vibration study. Again, we're going to use 15 natural frequencies because that covers at least 85% of our modal mass. And let's tell the software the limits of our frequency. Let's go from 0 to, let's say, 500 hertz just to save us some time. Typically, you go up all the way to the ends of your input curve, and our curve goes from 0 to 2,000 hertz. But let's just go up to 500 hertz just to run a nice quick simulation. And this is almost done. And now we're done. So with random vibration studies, the type of results that you get are going to be the RMS results, or the 1 sigma results, because it's a statistical type of simulation. So the RMS stress value, or von Mises value, is going to be 3.8 megapascals. Now, since this covers only 1 sigma of the results, that only covers about 66% of the time that your stress levels are going to be below 3.85 megapascals. What we want is going to be the 3 sigma results. In order to get the 3 sigma results, you basically multiply your results by a factor of 3. So even though our maximum stress level here shows 3.8 megapascals, if we multiply that by 3, you're going to get approximately about 11 megapascals. So you want to make sure you use the 3 sigma results, because this is a statistical analysis, and you want to make sure that you encompass about 99% of the load cases. Now if I double click on the displacements, the maximum displacement on this board is going to be 0.18 millimeters, and that's going to be your 1 sigma result again. So most people again want to take a look at your 3 sigma results. So we want to multiply this maximum value by a factor of 3. And so our actual deflection that you want to compare with the allowables is going to be about 0.55 millimeters, about half a millimeter. So again, you want to just make sure that that maximum displacement on this circuit board stays below the allowable displacement that you get from the Steinberg equations. So let's do one more thing here. Let's take a look at the acceleration plot. And this is what our accelerations look like. Let's go ahead and probe the results at the 4 different chip locations. And so maximum results that we're getting here is about 243, actually about 224.3 Gs. Okay, let's come back into our PowerPoint presentation. And that's our random vibration simulation. Let's now switch over to our harmonic analysis. So harmonic analysis assumes constant amplitude excitation. It's typically used for simulating frequency sweeps and determining your transmissibilities. So if you have a load that's oscillating at a certain frequency, you can actually change that frequency however many times you want across your frequency range, and you can find out what the maximum response of your structure is going to look like. So this is just a nice, easy way to find out the sensitivity of your structures and the amount of displacement versus your frequencies. So let's switch over into SOLIDWORKS and I'll show you how to do a harmonic simulation. And so I'm going to create a new study. This one's going to be called harmonics. And I'll click on the linear dynamic option and click on the harmonic option. And just like before, we get a feature manager called harmonics, and what we want to do is we just want to step down that feature manager. We're going to skip the parts folder, we're going to skip the connections folder because they've already been defined, and we're going to stick with the defaults. For the fixtures, we're going to come down to one of our previous studies. We're going to take the fixtures and we're going to drag it and drop it from one study to the next. I'll come down to the external loads folder, and again we're going to do a nice uniform base excitation, and that base excitation is going to be in terms of the acceleration levels, and I will use the top of the board as my reference direction. Let's change the units to Gs, and I'll put in a multiplier of 1G, and we'll click on the curve option just like we did before. I'll change the units to Hertz, and let's come back into Microsoft Excel where I've got the curves already defined, and in this case we've got just a nice uniform curve. We've got 10 Gs from 0 to 2000 Hertz. So let's go ahead and copy this curve. I'll come into SOLIDWORKS again. Let's paste it in. And let's click on View, and we just got a constant 10G load. I actually didn't have to put in a curve option. I could have just stuck with the linear option, and that would have been 10 Gs. Okay, let's keep stepping down the feature manager. The next option is going to be the mesh folder. So let's come back to one of our previous studies. We're going to drag and drop the mesh from one study to the next. And let's come back down to our damping option. Let's drag and drop the damping settings from one study to the harmonic study. And let's change the properties of the simulation. And again, we're going to use 15 natural frequencies because that covers at least 85% of our modal mass. And let's tell the software that we're going to do the simulation from 0 to, let's go up to 500 Hertz. Again, our load curve goes up to 2000 Hertz, but let's just go up to 500 just to save us some time. Let's go ahead and run the simulation, and we'll let it run. Okay, so now the simulation is done. Now the stress level that you're seeing is going to be about 1 megapascal, but that's going to occur at 500 Hertz. Let's take a look at our displacements. The maximum displacement that we get here looks like it's going to be 0.027 millimeters, but that also occurs at 500 Hertz. Typically you want to find out what the results look like across the different natural frequencies. And so what I'll do next is I'm going to go ahead and let's go ahead and probe the results. Let's use our sensor locations on the chips, and let's go ahead and plot the response curve. And this is what your dynamic response looks like, or your harmonic response looks like for this particular board. So notice the x-axis is going to be the natural frequencies, and we did a simulation between 0 and 500 hertz. The y-axis is going to be the actual displacement. And notice at the first natural frequency, which occurs at about 284 hertz, the maximum displacement that we're getting is about 0.4 millimeters. So what this tells us is if we take this board and we shake it at 284 hertz at 10 Gs, our maximum displacement is going to be 0.4. Now, if we take this board and we shake it at about 345 hertz, the maximum displacement that we're going to get is going to be about 0.09 millimeters. So basically, this is what a harmonic simulation does. It lets you sweep across your frequency range and find out how much deflection or how much stress or how much acceleration you're going to get based upon an input load at these different frequencies. Okay, let's switch back into our PowerPoint presentation. Now, performing simulations helps you reduce the cost of prototyping. So let's consider the following case. Let's say your initial physical prototype takes about a week to build. In order to test it, it's going to cost you labor costs of about $800 and hardware costs of about $2,000. For each additional design iteration, it's going to take you an additional day to build and test, or modify and test, which is going to cost you at least $800 in labor costs per day and an additional $500 in hardware costs. So for 6 different design iterations, you're looking at about 2 weeks and about $10,600. With simulation software, you can actually create virtual prototypes. And with virtual prototypes, you don't have to wait for any machining time. You can actually test your solid models directly on the computer. So your initial prototype and the initial setup may take about 4 hours. Labor cost is going to be about $400. It doesn't cost you any hardware costs. For each different design iterations to modify your mesh or modify your loading conditions, let's say conservatively, it may take you a couple hours, which means about $200 in cost. So for 6 different design iterations, you're looking at about 2 days and maybe about $1,600. So virtual prototyping or simulations helps you to significantly reduce the time and the cost to validate your designs. So again, the software package that we used today was called SOLIDWORKS Simulation Premium, and we use the advanced dynamics capabilities, including time histories, harmonics, random vibrations, and response spectra. That's it for today's presentation. Thank you very much for viewing the presentation. My name and contact information is at the bottom right-hand corner of the slide. If you do have additional questions, please feel free to contact me, and we can discuss your simulation needs in more detail. Thanks again, everybody. Bye now.